And so I'm pretty sure we'll cover all this by end of the semester. Important thing is correlation function. Correlation function. When I say correlation function, it's a relation between the two random process or two random variable. Input, excitation to output responses, okay? And which you usually, I call RXX or RYY. X is something like excitation, for example. Y is response. And also RXY, which is all in time domain function. Okay? And another is all time domain, CXX, CYY, CXY. That's called the covariance function. This is XXYY is autocorrelation function, and this is called the cross correlation. Cross correlation. This is autocorrelation. Of course, I'm going to review quickly the one we have done last Friday, then move on. Okay? Because if I lose you here, then I'm going to lose you forever, which is bad. And the C is CXX is covariance, it's called. I'm not sure whether I covered this or not. It's called covariance. Okay? Covariance function. And this is called cross covariance. Cross covariance function. And also, so we're going to talk still, I have to clarify everything in the correlation and the correlation function. And another one, spectral density function. Spectral density function is like SXX, SYY, SXY. This is in frequency domain function. Powerful, very powerful, the expression to characterize the time domain function. Or if it's a dynamic problem, then you are really talking about the characteristics of the dynamic system. This is really reveals the dynamic system. So usually I insist to learn the spectral density function 100% correctly and exactly. In vibration class, toward the end of the session, you learn a little bit, but depend on the curriculum. That's my understanding is. But it has a very close relation between the correlation function and also the spectral function. And the relation between R, X, Y relationship. This is a time domain function. This is a frequency domain function. This is the relation. Anybody knows about this relation? Who involved in research in the vibrations and all that, a little bit statistics. This relationship is Fourier transform relations. What does it mean? Sxy f is equal to integration minus infinity to infinity, and R xy tau e to the minus 2 pi f tau theta. This is a Fourier transform of correlation function. Correlation is spectral density function. This is a frequency domain. This is a time domain. Okay? And vice versa. So once you know this, Rxy, of course, is a function of tau, is minus infinity to infinity Sxy f. This is inverse Fourier transform. E to the 2 pi f tau df. Inverse Fourier transform. Of course, if it's xx, it's going to be xx. Same thing over here. Time domain, this is a frequency domain. In addition, this is a Fourier transform. This is what mostly we are using it in the dynamic system to understand the dynamics of the given system. But of course, there are other kind of the transform. You know the Laplace transform. And what other transform? There are a few different transforms you are using. Somewhat, a little bit not like a Fourier transforms. Okay. Yeah, few more. So that's what I'm heading for right now. We started this a little bit. Then we're gonna do the spectral analysis using the spectral function. Then, so in old days, the revolutions came in. Revolutions came in 1966. Before, after is lightning occurs in 1966 when IBM, two scientists in IBM research lab in New York, corporate research lab, IBM research lab. I think I forgot exact name. I have to check. And LEY something like that. They developed, not invented. Word invented, you use to really create something new. But this is not to create something new, but invent is less level. They developed a process to do the Fourier transform in very fast fashion is called FFT. You heard about it? So fast Fourier transform. All the methodology to convert from time domain function into frequency domain function, incoming data is all analog data. It's continuous data, analog data. Nowadays, still some people, of course, may use analog data to process it, but convert into digital data, and that's much faster and easier. And before 1966, to get the spectral function, this is exactly what they have done. First, to get this, first they got this in time domain. They just develop classical way to compute the Rxy. Then take a Fourier transform exactly like this. But nowadays, no, they don't do that. It's not going this, then this. So use a fast FFT routine to directly get into frequency domain function, spectral function, much faster. Then to compute Rxy, what happens is first compute Sxy directly by FFT, then take an inverse Fourier transform to get Rxy. That's what we are doing nowadays. So all the testing instrument before 1966 is what they do. First compute Rxy, then take a Fourier transform. All the instrument, any machinery, that's what they do. From 1966, all the instrumentations are not doing this way. Take too much time. Compute FFT. Directly will show you. Then take inverse Fourier transform to get Rxy, Rxx, Ryy. So it's totally upside down. Since 1966, all the instrument that developed before 1966 has to be scrapped out. I happen to have one in my lab in Naval Postgraduate School out there. I kept it good. Then I have all the digital equipment. So this is what I'm gonna go through: direct approach, FFT approach. But FFT itself, algorithm is mathematical, then you can handle in a separate fashion. But it's in the textbook I mentioned to look at once in a while. They have some simple write-up, but still involved lots of different kind of the math you can take a look at. But I would rather concentrate on engineering, tie into statistics. So, but anyway, the roadmap is what this is. And so this chapter is dealing mostly correlated situation, how to handle the correlated situation. So that's what I started working on it. Then straight line kind of the approximation, which is called the regression line, based on the regression analysis. then develop the equation, right? So you could have a lot of data. That's what we have done last Friday. Then you can develop straight line. It's a best fit straight line. Then if you pick out any measured data, and this is a straight lined point along the line here, then I can say this is a difference between the measured data and the point in the best the line, right? So then what we did was, okay, let's take you're gonna face always expected value, which is really best approximation. Then you can say which is what? Which is what I say this is a y, right? Which is in there. So this line we call y is equal to mx, but this is a 0. Real data could be here, but anyway, we set the CEG point. This is a CEG point, right? We shifted out x and the y to the CEG point y. What's the reason? To make life easier, to set mu x, mu y is equal to 0. It makes it simpler. And over here, the m is simply slope. So this you call you call regression, right? Regression line of y to x, you can say that. Regression line of y cos, well, what I say that? I named over here regression line of y on x. So this is exactly that case on x. So that's what we have done last Friday. And so difference delta is equal to y. This whole thing is y. And this guy is mx, isn't it? Y minus, oh, I'm getting rusty on them. Y minus mx. So whole idea is to get the best m slope, right? So you take a derivative of delta with respect to m, right? Then set equal to 0. Then we got the estimate of the m, best fit m. So here, this equation is a beginning of regression line equation of y on x. So then we developed the equation. Best fit equation is e to the, it's a quick review, and bottom is e to the x squared x. I think you should exercise at home to derive this one. And over here, this, so assumption here is e to the x is equal to e to the y. Mean value of x and y is equal to 0. Why? Because we shifted down to CG. Got it? One of the assumptions is that. So here, e to the xy, anybody knows e to the xy is, what do you call? Sigma xy, right? This is what we covered already. And what do you call this? Anybody can tell what's a sigma xy? Sigma xy here is called covariance. It's not the covariance function, it's simply variance. And here, sigma xy is, as it shows here, this is called right here. And this is what the fact is. And E expected value of x squared is sigma x squared, which is a variance. Why called the variance? This case is mean of x and y are equal to 0. So if I rewrite this guy, sigma x squared, the definition is e to the but this guy is 0. In this case, so even if there is not, it's not the expression like this because mu x is equal to 0, then I can still claim that this is sigma x squared. Nothing to confuse. But start from this CG right here, right? Origin is a CG, that's what it has. So over here. So if I just rewrite here, y is equal to sigma xy, sigma x squared. I'm going to say put the x here. I'm going to say here. I'm going to add here. I'm going to add here. Simply add. No change. So I'm going to just rewrite this guy as a sigma xy and no change. So sigma x, I'm going to put sigma x, no change. So I'm going to just put this guy, exchange these two. So you have sigma xy, sigma x, put this guy here, sigma y, I'm going to put this guy back there, x, sigma x. Okay. So if I just rewrite here the relation y, sigma y is equal to sigma xy covariance sigma x, sigma y, sigma x, x. Of course, as a reminder here, mu x, mu y is equal to 0. In usually dynamic data, measured data, easiest way to simplify is first drop the static value out. Then you can deal with the dynamic value. Then later, just add the effect of the static values right into it. You don't have to really mix from the beginning. So that's what that is. And of course, this is a regression line of y on x. Then what about the regression line of x on y? Just to reverse it. Then all you have to do is reverse x and y. Okay? For that situations, this is a regression line of x on y. If you do that, then you have the x over sigma x is equal to sigma yx is xy, sigma x, same, no change, then y, sigma y, right? But this case is regression line, so which means here when you have this, you are talking about the measured that and measured this, not vertical. But now, to generalize it, this is a real origin where mu x is not 0, mu y is not 0. When you have all the correlated data, then all you have to do is change x to mu x. First, for the regression line of y, so y, this is sigma y, and this is minus mu y. So this guy, you have to change. This guy is e to the y minus mu y, take a square root. This you have to take a square. Variance, then change into standard deviation. When you want to include the mean value, this origin is origin of the data, is equal to sigma xy, sigma x, sigma y, and x minus mu x over the sigma x. So sigma x is like this, as I see here. So this is y. I'm sorry. Sigma y. Sigma y. So if I here, you have to be careful. So I'm going to write sigma xy is equal to e to the x minus mu x. Can you see it there? Not good, right? Not good. If you look at it, it's very logical. So xy is e to the x minus mu x, y minus mu y. Just like this. then sigma x is equal to e to the x minus mu x square, take a square root. Of course, the sigma y here is e to the y minus mu y, all that. And this is called what? Oh, it's called the covariance. And this is called correlation coefficient. That's the name. Correlation coefficient. That's what I spelled out here. So that's what I covered until last Friday. So this is just a review. All here. I want you to review up to here. Okay, page 9. I covered up to pages 8 or page 7. Then 8 and 9. I'm going to start tomorrow here. Because I repeat about the same thing which I covered the Friday. And give some thought. Rather than just the math. Math is simple, but get the engineering sense out of it. Okay? Then you will be more comfortable. So it's getting into correlation now. Correlation between x and y. Could be a random variable. There is a degree of correlation. And the degree of correlation we'll discuss tomorrow. Well, not tomorrow, Wednesday. So I'll move on. Still steady pace. Otherwise you will get lost. So steady pace. I'll try to get some engineering sense. And we'll share it together. And we're going to talk about this one. This is rho x, range of the rho xy. Correlation coefficient is -1 to the 1. It's a degree of dependency. Okay, we'll talk then. All right. So sorry today I become a little bit late. Sometimes we have to do. So I'll see you on Thursday.